Right, so begins our foray into Newton's laws of motion. First, a little background. Newton was an English dude and a mathematician and a scientist, and he was famous for discovery of the law of gravity, and he also discovered the three laws of motion. There's that whole thing, apple falling, hitting him on the head. Probably didn't happen, but it's a good story, but that's that guy. He published him in some book with a really long Latin name in 1687, which was, not so long ago, but still long ago that, he's dead now. And today these laws are known as Newton's laws of motion, and they describe the motion of all objects on the scale we experience in our everyday lives. So that just means big things, like anything bigger than, a grape. Well, probably some things a little smaller, but nothing down at the molecular level. That's all quantum mechanics. All of Newton's laws break down at the microscopic level. So it's only for big things like, people, cars, planets, stuff like that. Here's a little quote by him. If I have ever made any valuable discoveries, it has been owing more to patient attention than to any other talent. So it doesn't matter how smart you are. If you don't pay attention, you're not going to get stuff. You're not going to make discoveries. Nobody's going to remember your name after you die. So here's Newton's laws in a nutshell. Here's all three of them. And I will go over in more detail each one. So the first law is an object in motion tends to stay in motion, and an object at rest tends to stay at rest unless acted upon by an unbalanced outside force. I'm going to include the word outside, because there could be unbalanced forces inside of the object. Second law, force equals mass times acceleration. Newton's second law is this equation right here. That is Newton's second law. F equals ma. You're going to be using that equation a lot. Luckily, it's only three variables. And the third law, for every action, there's an equal and opposite reaction. I punch a wall, the wall punches back at me with the same amount of force. I kick a stone, the stone kicks me back with the same force. So Newton's first law, again, it's an object at rest tends to stay at rest, and an object in motion tends to stay in motion unless acted upon by an unbalanced force. So what does this mean? Basically, an object will keep doing what it was doing before unless acted upon by an unbalanced force. So if an object is traveling at a constant velocity through outer space, it'll keep traveling at that same velocity until something outside acts on it. It could also mean if something was sitting still, it will remain sitting still unless, something pushes it or kicks it or, shoots it with a, cannon or something. So you sitting there watching this, it takes a force to get you to move, which is the last little bullet. It takes a force to change the motion of an object. So what is meant by an unbalanced force? If the forces on an object are equal and opposite, they are balanced. So if this much up equals this much down, the net force, let's say this is 20 newtons, this is 20 newtons, and then we're talking about the net force. Net means the sum of all the forces. So we add up all the forces. So we know things going up are positive y, things going down are negative. So it's 20 newtons up plus 20 newtons down, which is minus 20, because it's down, equals 0. Balanced. If they are not equal and opposite, then the forces are unbalanced and the motion of the object changes. So let's say, for instance, this guy's still 20 newtons, this guy's still 20 newtons, but I go to pick this book up, and I supply a force of 15 newtons more upwards. So now my net force equals 20 newtons plus another 15 newtons up minus 20 newtons. So my net force is now equal to 15 newtons up. I always want to get that direction too, because forces are vectors. Force is a vector. That means it has magnitude and direction. So that's why I included this up. That's why this is negative, because it's going down. Remember that. I always need a direction. Some examples from real life. So, soccer ball sitting on a soccer field. It takes the unbalanced force of a kick for it to move. Some people playing tug of war. They're both exerting equal forces on the rope in opposite directions. So nobody's going to win this guy. The little flag that should be here, to signify the winner, isn't going to move because these people are pulling this way with 400 newtons, and these people are pulling this way at 400 newtons. So if there's no unbalanced force, then no motion will be changed. Newton's first law is also called the law of inertia. Very important word. Inertia is the tendency of an object to resist changes in its state of motion. So the first law states that all objects have inertia. The more mass an object has, the more inertia it has, and the harder it is to change its motion. I always like to equate this to football. Who are the fattest football guys on the field? Usually the offensive line. Now, the offensive football players are fat because people are trying to get through them to get to the quarterback. And since they're so fat, it's hard to change his motion, harder to change the fat guy's motion. So that's why you want your offensive lineman to be really fat on a football field. Now, the skinniest, most agile guys are usually the wide receivers. They can run really fast, they can turn really quickly, make all kinds of crazy moves. They can run this way and cut back real quick. This is because, so you want skinnier guys, faster guys to do this, because the skinnier you are, the easier it is to change your motion. They have less inertia than the fat lineman. That's how I equate that to football. Since it's football season, I feel it's appropriate. So some more examples from real life. A powerful locomotive begins to pull a long line of boxcars that were sitting at rest. Since the boxcars are so massive, they have a great deal of inertia, and it takes a large force to change their motion. And once they're in motion, though, it also takes a large force to stop them. So if you've ever seen a train start up, it starts off really, really slow, then picks up speed. But if you're trying to cross the train tracks and there's a train coming, I really doubt it's going to be able to hit the brakes in time to be able to slow down, because it takes them a long time to slow down because they're so massive. So it's going to take a lot of force to change their motion for them to slow down. So on your way to school, a bug flies into your windshield. Since the bug is so small, it has very little inertia and there's very small force on your car. So small that you don't even feel it. That's why those bugs get splattered. So even though the bug hits your windshield, here's your windshield, here's a bug, it's going to be an unbalanced force. This guy's going to hit here, this guy's going to hit here, splat. So that's why the bug just kind of explodes, because you're hitting with such a large force because you have such more inertia. Now the actual force between the bug and the car, though, is going to be equal for Newton's third law, which we'll talk about when we get there. So if objects in motion tend to stay in motion, why don't moving objects keep moving forever? Good question. Things don't keep moving forever because there's almost always an unbalanced force acting on it. So you're driving in your car and you let up the gas, you're eventually going to slow down. Now, why is that? Probably has a lot to do with how fast you're going. The faster you go, the more air resistance there is. The more air resistance, the quicker you're going to slow down. There's also lots of friction acting in the engine and between the bearings on your wheels, so the little frictional force is also going to slow you down. You could be going uphill, that's going to slow you down even quicker because you have more force acting down the hill than up the hill. So also things that are sliding, like a book sliding across the table slows down because there's friction pulling it down. That little mini lab we did at the beginning of the year, put that wax paper into that book, decreased the friction so it slowed down, took longer to slow down. If you throw a baseball upwards, it'll eventually slow down and fall back because of force of gravity. Gravity's stronger than the force that you applied to it. So it goes up, reaches maximum height, but since gravity is so strong, it's eventually going to slow that ball down. It's going to come back down to the earth. It's going to change its motion. So in outer space, away from gravity and any sources of friction, a rocket ship launched with a certain speed and direction would keep going that same direction and speed forever. because there's nothing in space to really slow us down. There's no air, so there's no air resistance. Now that rocket will go on forever, unless it comes close to a big star or a planet or something. But space is so empty that that's not very likely. So that rocket will actually go forever and ever and ever. You just give it like one little push. And there goes the rocket. Bye, rocket. So Newton's second law is force equals mass times acceleration. F equals ma. That's all his law is. F equals ma. And if we remember from our kinematics that acceleration is a measurement of how quickly an object changes its speed, which is why it has units of meters per second. It changes its velocity a certain amount in meters per second every second. And we can also write that as meters per second squared. So what does F equals ma mean? It means that force is directly proportional to mass, because, it's on, pretend like this is over 1, directly proportional to mass and to acceleration. That means that if mass gets bigger, force gets bigger. Acceleration gets bigger, that gets bigger. Mass gets smaller, smaller. Acceleration smaller, force is smaller. So imagine a ball of a certain mass, maybe got a certain acceleration. The ball has a certain force. Because it has mass, it has acceleration. Gotta be a force. Now imagine we make the ball twice as big, we double the mass, but keep the acceleration constant. Therefore, you're going to have twice the force. So you're going to have force equals 2 times the mass times acceleration. And since it's directly proportional, force is directly proportional to the mass, we also have to put a 2 in front of here. Anything we do to the mass, we have to do the same thing to the force. Anything we do to the acceleration, same thing to the force. So now imagine the original ball moving at twice the original acceleration. So this time we have F equals m times 2a. Gonna have to put that 2 there again, because force is directly proportional to mass and acceleration. So if you double the mass, you double the force. If you double the acceleration, you double the force. What if you double the mass and the acceleration? 2 times the mass times 2 times the acceleration is going to equal 4 times the force. 2 times 2 is 4. 4 forces. So doubling the mass and the acceleration will quadruple the force. Now what if I had half the mass and double the force? Oops, sorry, double the acceleration. 1/2 times 2 equals 1. So still the same force. So what if you decrease the mass by half? I just said that. Well, actually I did decrease mass and increase acceleration. So let's just decrease the mass. So you have 1/2 mass times acceleration. Since they're directly proportional, you're going to have 1/2 the force. So F equals Massachusetts basically means that the force of an object comes from its mass and its acceleration. Forces are produced by accelerations, or accelerations are produced by forces. Something very massive, meaning it has a high mass, that's changing speed very slowly, which means it has a low acceleration. Like a glacier can still have a great force. That huge mass, even though acceleration is low, is still going to result in a great force. Bye, Mr. Glacier. I'm not going to see you for a while because of global warming. So something very small with a low mass that's changing speed very quickly, a high acceleration, like a bullet, can still have a great force because it has such a big acceleration. But if it's something very small, changing speed very slowly, it's going to have a really weak force. Like if I just threw that bullet at you, it's not going to hurt as much as if I shot it at you, because it has less acceleration if I just throw it like with my hands. And now Newton's third law, 3, it's the magic number. For every action, there's an equal and opposite reaction. So what does this mean? For every force acting on an object, there's an equal force acting in the opposite direction. Right now, gravity is pulling you down. Gravity, the force of gravity, our weight is a force. And it's pulling us down in our seat right now. But Newton's third law says your seat is pushing up against you with an equal force. So this is why we don't fall through our chairs, because the seat's pushing us back with the same amount of force we're pushing down on it. So there's a balanced force acting on you, gravity pulling down and your seat pushing you up. So think about it. What happens if you're standing on a skateboard or a slippery floor and you push against a wall? Obviously, you're going to slide in the opposite direction away from the wall because you push on the wall, but the wall pushed back on you with an equal and opposite force. Yes, walls push back. They don't like to be pushed around. So why does it hurt so much when you stub your toe? Because when your toe exerts a force on a rock, the rock exerts an equal force back on you. So the harder you kick that rock, the harder it's going to hit you back, and the more it's going to hurt. And just a little review. Newton's first law. Objects in motion tend to stay in motion, and objects at rest tend to stay at rest unless acted upon by an unbalanced outside force, also called the law of inertia. There's that really annoying bell. Somebody just died. Poor soul. And Newton's second law, force equals mass times acceleration, F equals Massachusetts. And Newton's third law, but not the least important. For every action, there's an equal and opposite reaction. Some new vocab we learned today. Inertia is the tendency of an object to resist changes in its state of motion. Acceleration, you should already know this, is a change in velocity. It's a measurement of how quickly an object changes its speed, direction, or both. Now this direction is going to come in real handy when we talk about rotational stuff. And velocity, which we already know, is the rate of change of position along a straight line with respect to time. So how much distance it covers divided by how much time it took. And force. Force, we're talking about strengths and energies, a push or a pull. I like that too. A push or pull. That's all we're really doing, is pushing things and pulling them. That's it, thank you.